So our t value, because the sample is less than 25, our t value, sample less than 30. So our t value is going to be x bar, which is 172.1 minus the claim. The claim is that it is 170. So that's 170 divided by the standard deviation, which is 7.6 over the square root of 25. So when we put that in the calculator, we get 2.1 divided by 7.6 divided by 5. You get 1.381. All right. So our first job is to set up state the hypothesis. So our second thing that we have to do is calculate. So the first thing you do is determine HO and HA, determine what our hypothesis is. So then the next thing is to calculate T.
Sir, sorry to interrupt. Is it possible for you to record this meeting?
Them remove the thing because true we don't pay them any more money. They remove the ability to record. I was trying to find another way to record, but when you look, the recording option is that them take it out because. So I don't know how. I was being told of another way to record the thing, but I don't know of any. I don't remember the method. Does anybody know how to record other than?
Yes, sir. OBS Studio.
Huh?
OBS Studio.
Oh. So Windows plus G. Somebody else can record it because it's a Windows plus G, but or I don't know how you do that because I tried it and I don't see anything happening. Is there anybody else who can record what is going on? All right. All right. All right. So the first thing that we have to do is formulate our hypothesis or null, and second thing is to calculate the ZRT value. We said that if the sample is less than 30, T, if it's greater than 30, Z, that kind of is the rule. We're going to expand on that a little bit. So the next part is now, last week we had said that given, when we are given, not given the limit for the test or the critical value for the test, it is always 95%. But we can determine whether or not we want the critical value to be greater or less. But the bigger the value that we put on it, So we ought to be 99% sure or 95% sure or 99.5% sure. Then um, we the all that is going to happen is that the table value that we're going to look up is going to get larger in most cases. So the third part of it is to look up tabulated value. %95%. We're going to use 95%. This is the default value. So then we get the T table. Of course, you can get the T table online. All right. So our T table, what we said that we would do is that our tabulated value of T at 95%. What when we look at the T table, what we have to do is work out degrees of freedom. And we said last week that the degrees of freedom for this particular thing is equal to n minus 1, where n is the number of data points. 25 in this case.
Excuse me, sir. Isn't there a possibility that we can have access to your whiteboard? Like send us a link to it?
I did that last time. I don't know. Yeah, we'll give it a try. All right, so let me just do that hypothesis. Give it the title. And then yeah. Um, Give me a second here. Let me just sort out that housekeeping matter. All right, so at the end, I will just export it, and I will also provide the link. Need to find out. Remember where to find the link, but I will find the link. All right, so I will give you access to the board as soon as we finish. All right, so the number of data points that we have. In this case here is 24. 25. So what we are going to do is look under 25 minus 1 in the table. So we're going to look at 95% under 24 in the table. All right. So we'll go to the T table, critical values for the T distribution. We'll find 95% at the top of the values, and then we'll go down to 24. So 95 is the third column, and 24, under 24, we see 1.711. So the critical value is 1.711. So let's write down that. So our calculated value is 1.381, and our tabulated value is 1.711. So how does that help us to make our decision? Well, the simple way to treat it is that our tabulated value said that 1.711 is the border. So this is HO, and over here is HA. All right. The original test says greater than. So this sign here always points to where HA, where you're supposed to look for HA. So HA, we see that HA is that mu is greater than 170. So this is our section which it's pointing to for HA. Or HO is over on this side. Now 1.381. Where does that lie? Well, it lies in our HO section. It lies somewhere over here. HA, the borderline is 1.711. So therefore, we do not have enough evidence to reject HO. So that is lawyer speak for say that we do not to reject, to accept HA. Sorry. Because it lies in the HO region. So we accept HO, the mean has not changed. So the fourth thing that we have to do, make a decision. So first, we have to formulate our hypothesis. Second, we have to calculate our t-value. Third, we have to look up what is the critical value. And fourth, based on the calculated value and the critical value, then we have to make a decision as to whether we accept or reject. So, any questions on that? Yeah, so let's put up another question. All right. So the next question was, manufacturer claims that the thickness of the spearmint gum that it produces is 7/5 hundredths of an inch. The quality control specialist regularly checks this claim. On one production, take 10 pieces of gum and measure their thickness, and these are the values that he obtained. And then now they want to check. So the thing is that if he's manufacturing and say that the thickness of the gum, our null hypothesis is that mu is equal to 75 hundredths of an inch. So that is 7.50. We're just going to use 7.5 one hundredths of an inch. We are assuming that the thicknesses these are all 100ths of an inch. And the alternate hypothesis now, it's manufacturing. So if it is greater than, it's going to be a problem because you're going to be losing your profit because you put in too much here. And if it's less than, then the quality is reduced. The quality is not what it should be. The quality says that the quality control says that the thing should be 7.5 one hundredths of an inch. So if it's less than or greater than, then it's going to be a problem. So our alternate hypothesis is that it's not 7.5 one hundredths of an inch. So that's why we put the not equal to. Now this, when it's less than, it's called a one-tail test. This now is called a two-tail test. And two-tail because we are concerned both whether it is less than or greater than. Either way is going to be a problem. So this is a two-tail test. So we are going to be examining both ends of the spectrum to see. Is it bigger than? Or is it so once again, we're going to put in our T. So this is first one, is that we have to formulate our hypothesis. So the next one is what we are going to do is calculate so one is formulate the hypothesis, two calculate, in this case, t value. Example, less than 30. So we need to find so we're going to go type in the 10 values that we have. So let me just write them down here. All right, so our values are 7.65, 7.60, 7.65, 7.70, 7.55, 7.55, 7.4, 7.4, 7.5, 7.5. So once again, we're going to find the mean, and the standard deviation. And so this is 0.102, 7.55. So x bar equals 7.55 and standard deviation is 0.102. The mean the claim is 7.50 and the number in the thing is 10. So t is going to be equal to 7.55 minus 7.50 divided by standard deviation 0.102 divided by square root of 10. So 7.55 minus 7.50 divided by 0.102 divided by square root of 10. Somebody check this for me and see if we get the same answer. 1.55. So my calculated value is 1.5.
Yes, sir.
So my tabulated value. Again, we're going to use 95%, so that if we perform this thing 95 out of 100 times, the result is supposed to be the same. At minimum 95 over the 95%. And degrees of freedom is equal to 10 minus 1 equals 9. So our tabulated value is, we're going to look up 95 under 9. Now, remember last week we said no for two-tailed test, 95% means that over here is 2.5 and over here is 2.5. But we're looking at both ends. But the table, you look at the top of the table, it only gives one piece. If you're looking at the curve, the gray shaded area covers everything going back. So it only gives one piece. So the gray shaded area, it only gives one piece. So we have to be cognizant of that. So 5% mean 2.5 over one end and 2.5 over the other end. So what we're going to have to do is look up everything from here going back. So this is going to be 0.975 because we're only looking up 2.5% as one half of the table. So we're going to look up not under 0.95 because of two-tail test, but under 0.975. Or we'll look under 9. And when we look under 9, we see 2.262. So our T tab is 2.262. So now, the calculated value, the borderline is 2.262, and what this side is minus 2.262. And so this is where HA is. HO is in the middle. So now, for this, again, our calculated value lies in the HO region. So our conclusion. Accept HO. The mean has not changed. So one, formulate the hypothesis. Two, calculate the value. Three, look up the tabulated value. So once you have a calculated and our tabulated value, so calculated, tabulated, then we are in a position to make a decision. So any questions on that? All right, let's do one more difference. We'll bring in this question. All right. What is not obvious here is what the question is. They want to measure um, one way to measure a person's fitness is to measure percentage body fat. Average body fat percentages vary by age, but guidelines say that the normal for men is 15 to 20%, and for women is 20 to 25%. They give data from men and women who work out 3 times a year. Trainer measure the body fat, and the table shows the data. So um, so the men, the data for the body fat is given, and for the ladies, the data for the body fat is given, but it's not so clear because only cut out part of it was what they wanted to find out. So what they said that they wanted to find out, but I'm going to be changing it. Where the question says that they want to find out if they statistically, if the body fats are equal, but then so they want to find. Well, let me do that first because that is an easier question to do. So our HO in this case is mu. The two means are equal. HA, what we want to find out is if the two means are not equal. The other way of writing this is HO, this difference of the means, equals 0. And HA, the difference of the means, is not equal to 0. So in other words, what we are saying is that is the body fat that is seen in women equal to the body fat that you see in the men after they work out at the gym? Well, my cursory look at the data would tell me that the women greater than the men. But then statistically, maybe that is not so. So what we're going to do, here is the thing now. Our t value is going to be, for this particular thing, x bar 1 minus x bar 2 minus mu 1 minus mu 2 over. Now, the statistic that we use for that. So there's remember the first one is x bar minus mu, but we're talking about the two now. So we have to use x1 minus mu, x2 minus mu. So we have this situation here. Now, when we pull the things together, our standard deviation is going to be, let me write it down. Well, you have different models that you use. So let me write down the simplest one. S1 squared over N1 plus S2 squared over N2. So is the sum of the standard deviation over N1 plus N2. So that is the statistic that we have to calculate. And this statistic we can look up. And what we need to be able to do is understand what t-value that we need to calculate when we're looking for a comparison between means. So this is our calculate our t-value. All right, so let's calculate the mean and the standard deviation. So we're going to list them in our table once again. By the way, you're still there, or am I talking to myself? Okay, so I'm not talking to myself. All right, so let's notice I never answer that part. So let me just fill in the values again. 13.3. So what I'm at pains to point out is that the statistic that you have to look up and calculate, the x mod minus x2 bar minus mu over sigma, whatever. They're big long formula, and to be certain, it is just that whenever you are going to calculate this test statistic, you look it up. So it's 13.3, 6, 20, 8, 14, 19, 18, 25, 16, 24, 15. That's a 1. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All of them says 10 each.
Sorry, you're working it out on a different window?
Oh. Sorry about that. All right, 13.3, 6, 20, 8, 14, 19, 18, 25, 16, 24, 15, 1. I don't know how that bridging must look. And percent body fat. And then 22, 16, 21.7. 21, 30, 26, 12, 33.2, 28, 23. One, two, three, four, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we're going to find the mean equal average equal standard deviation equal average equals standard deviation Okay, so let's go back. So let's write down what we have here. So we have x1, x2, s1, s2, n1, n2. So x1 and x2 14.94 and 5 and 22.29. 14.94, 22.29. This is 14.94 and 22.29. N1 is 13, N2 is 10. Standard deviations 6.84 and 5.32. 6.84 and 5.32. All right. So we can fill in the values here now. So T is equal to 14.94 minus 22.29. It didn't matter which one we call X1 and X2, as you will see in a minute. Minus. Now, here's the thing. These two means, according to our null hypothesis, the difference supposed to be equal to 0. So, so this here anyhow, this here is equal to 0. So is that minus 0. We said that the two means are equal. Divided by 6.84 squared over 13 plus 5.32 squared over 10. So this is going to be our t value. And like I said, it doesn't matter which one we put first and which one we put second, because whether positive or negative is going to be the same in the calculation. If you had put the 22.29 first and the 14.94 second, you'd get a positive result, and that would have mean something else. It would still be the same. Well, when we do the calculation, I'll show you what I'm talking about. All right, so 22.29 minus 14.94 . (6.84) squared so this will give me 3.6 basically, plus 5.32 squared divided by 10. It's 2.83. Somebody check us if it's 2.89. Basically 9. Somebody check and see if that is the answer they get. Yes. Anybody checking?
So I got negative.
Huh?
I got negative.
Oh, negative. All right. Now tabulated value. This is a calculated value. So now we want it tabulated. Now, when we have two set of data comparing, the degree of freedom, we say is n minus 1, but now it's n1 plus n2 minus 2. All right, so add the two set of data that you're looking at together. Remember, say each of them will subtract 1, so you add the two of them and subtract 2. So in this case here, it's going to be equal to 13 plus 10 minus 2. That's 21. All right, so T, I'm going to use at 95% as usual, and 21 degree of freedom. So we're going to look up that in the table. So once again, it's a two-tailed test. So we're going to, so let me go back here. So it's a two-tailed test. So at 95%, we are going to be looking, this is 2.5 over here, 2.5 over here. So at 95%, we are going to be looking at everything over here. So this 0.975 we're going to be looking at. And 21 is the value. 21 is the degrees of freedom. So degrees of freedom, 21, and we're going to be looking at 0.975. 21.975 is a foot. So this is 2.080. So our borders are 2.080 and negative 2.080, or HO is in the middle here, and over here is our HA. Now our 2.899 falls over here. So what that says is that we are going to reject HO. And HO says that reject HO, that the means are equal. All right. Now, persons will say, but we're going to look at the data and see that. Yes, sometimes it is obvious, but sometimes it is not. All right. We could look at this data and say, but these numbers don't suggest that. It suggests that we could have done a one-tail test that says mu1 is greater than mu2. All right. We could have done a one-tail test that says, sorry, that mu1 is greater than mu2. Mu1, the mean of the men is less than the mean of the women. We could have done a one-tail test. All right, but for the purposes of the discussion, we did a two-tail test. All right, so this is one of those problems where our null and alternative hypothesis is going to be based on the type of discussions that we have with the persons who are trying, whatever it is that they're trying to find out with the data. And we just passed through a season, a 2.5 year season, where people were quarreling over these type of tests. And saying all kind of things about different kinds of tests. But the general idea is what we're looking at here, that the means are equal or the means are not equal. So I want to spend sometimes and do one more question. But let me just illustrate one example of one of the arguments about that was carried out. All right. I know it's a controversial season to go back to, but with COVID, doctors carried out a test on hydroxychloroquine, some French doctors. I don't know if anybody remember that argument and that fuss. Whether you should use it or not use it. Anybody remember that whole argument?
No, sir.
And remember the one about ivermectin? But anyhow, so let me.
Repeat
Yeah.
that.
Huh? Sure, don't remember the argument about
That's
ivermectin.
you said.
Huh? When we explain the hydroxychloroquine, the Africans were using hydroxychloroquine so that they find that it helps with COVID. The French, some French doctors and some African doctors carried out a test. The objection to the test and the test results statistically were that the samples were incorrectly taken. First thing, them say N1 and N2 were not equal. But we have statistics to deal with whenever the two samples are not equal. The next argument was that what had happened was that the doctors had come in and the doctors had said that if you came in and you were sick, they would offer you the medication and you could refuse or not. So the sicker, older patients were the ones who usually opted for the medication, and the younger, not so sick ones were the ones that said, no, we're not going to take it. So the objection was that it was one sample was older and sicker, and one sample was younger and not so sick. And they carried out all of the same tests that we are carrying out here and talking about. And what they found out at the end was that the older sicker set recovered at a better rate than the younger not so sick test set. But the objection was that these two samples were not the same size. And the other objection was that one set knew that they were taking medication and one set knew that they were not taking medication. So that might have biased the whole entire operation. Meaning that if I know that I'm taking medicine, then I am more likely to feel better, say that I feel better than if I'm not taking medication. So all of those factors combined, like I said, it was one huge unstatistical discussion. So when I say unstatistical, because first of all, the samples don't have to be equal for you to carry out a statistic to find out if one is doing better than the other, and so forth and so on. So all of these things, calculations that we are doing, you find that they do a lot of these calculations in a lot of fields to verify whether something is as stated. Medication, whether the mass of whatever material or whatever it is that you are looking at, or the thickness or the length or whatever it is. Take a sample, take the average, take the standard deviation, and then test the hypothesis. And statistically, you're supposed to be able to say 95 out of 100 times, the value is going to be X. The mean is going to be X. There's 5 out of 100 times that the mean is going to vary from what it is. So people who are in manufacturing use these statistical tests all the while a hypothesis test to verify the validity of their samples or what to be able to say what type of sample they have or what type of sample they are looking at statistically. All right, so we're going to stop it there today. Feel like a fever coming on.
So you can scroll down to the last part of that question. Right here.
Yeah, like I said, we're going to stop here for today. I see a question being asked about tests. So yes, Mr. Clark.
Yes, sir. For the tutorial last week, you said you're gonna send a template.
Yeah.
Did you somehow send it?
No, I didn't send it. I
Oh.
was delinquent.
Okay. I
Very
was just checking.
delinquent. I will send it as soon as we finish here.
Okay.
I have it is just like I said, very delinquent. Whole parting and stuff.
All right. Cool.
So I send a template to say what I want to want in each. The test should come after we finish the third topic, and this is the third topic. So next week Monday, let us discuss where and what form the test should be. Is that not care a lot these days? So when we come next week Monday, we can decide what format the test is going to take.
Okay.
All right, with everybody.
Yes, sir. Yes, sir.
Sir, we're not having an upgraded assignment outstanding.
No, not so. Apart from this one, and then I'm going to give you a statistical one to do. And then one more. No, you don't have any outstanding assignment.
Question.
Mm.
So question about the outline that you said you was going to give us a canvas for the previous lab. Is that still going to happen, sir?
One again?
So remember you said you gave us an outline for the previous lab that we did? That was the last
Yeah.
2 weeks ago, sir.
Oh, it says my delinquency that caused it not to be done.
Okay, so can we expect that this week or early next
Yeah.
week?
This week.
Okay, all right.
This week. Today.
Oh, as in, and also, sir, for the lab, sir, is it supposed to be done as a group or individually?
I would like it done individually, that it can be discussed or whatever it is. But when you take your data and do whatever you have to do with the data.
Repeat that last part, sir.
So I don't mind if it is have a discussion, but everybody go hand me something. That one thing with 5 names on it. All right, but it's not a matter that I'm going to be saying that, oh, everybody must have their own thing. But I want to be able to say this is what this individual did.
Sir. So is when everything due?
Huh?
When
When this one
everything
and the next one due,
Mm.
when I give you the template
Okay.
in about, well, by the end of the term. Write it in the return. Right. So when you give it a template, you just need you to be working on it, and then like I said, we're going to give you a statistical one, and we need you to be working on that one as well. That one's supposed to be easier. 2 questions that we need to ask you there. And again, we give you a template and ask you to fill out. All right. Any other question? All right. If not, we're going to stop here for today.
All right, sir.
All right.